Hello, and finally, we're going to take a look at the unification of electricity with magnetism. On the screen, you can see an animation of an electromagnetic wave, and you'll see that there are these orange arrows that represent one of the fields, either the electric or the magnetic, and the blue represents the other. A couple of things that you'll notice. They all seem to be propagating in the same direction, and the field in blue is perpendicular to the field in yellow, and both of those fields are perpendicular to the direction of propagation. This is the hallmark of an electromagnetic wave, and we're going to be developing this concept over the course of the next little while. Now, why should there exist an electromagnetic wave at all? Let's go back to what we know. We know that if there is a magnetic field that changes in time, it's going to create a magnetic flux through some region, cross-sectional area A, that is also changing in time. The fact that the area is experiencing a changing magnetic flux means that there is going to be a voltage in that region. That's from Faraday's law. Well, if there is a voltage, it must be because there's an electric field. So what we have is that a magnetic field that changes in time creates an electric field. Not just a voltage, it creates an electric field. So one type of field creates another type of field. It was thinking along these lines that got Scottish physicist James Clerk Maxwell to fully investigate and unite the phenomena of electricity and magnetism. James Clerk Maxwell himself was a brilliant scientist. He was also extremely influential in the development of thermodynamics, and it's really quite a shame that he died so young. Now, what Maxwell did was he took Faraday's law and, just like we discussed earlier, said, well, okay, a changing magnetic field creates an electric field. That's what Faraday's law says. But Maxwell decided to turn that idea around and ask the question, can an electric field that's changing in time create a magnetic field? And it's not going to should surprise you that the answer is going to be yes. But in fact, we didn't need this discussion on Maxwell to figure this out. What we know is that electric currents give rise to a magnetic field. Well, an electric current is just a bunch of moving electric charges. So even a single moving electric charge is going to create a magnetic field. Well, let's think about that in a slightly different context. If I have just a single electric charge, that's the source of an electric field. So let's imagine that we had a single moving electric charge. So we're standing off someplace, and we have our handy-dandy electric field detector, and this single charge approaches us and passes by us. And our handy-dandy electric field detector is always going to be registering a changing electric field. Well, at the same time, our handy-dandy magnetic field detector is going to say, oh, look, there's a magnetic field. Because there's a moving charge, we are going to sense a magnetic field. So this might seem like it's reversing cause and effect or completely separate things, but Maxwell argued that we can interpret this as saying a changing electric field creates a magnetic field, just as Faraday's law earlier said a changing magnetic field can create an electric field. Now, here are a couple of questions for you to chew on just a little bit. Make sure you understand the idea of what I was saying on the previous slide. Suppose you are an observer and you are holding a barred magnet, and you're moving around, you're holding that barred magnet next to you. You have your handy-dandy electric field detector, you have your handy-dandy magnetic field detector. As you move around with this bar magnet in your hand, what do your handy-dandy detectors detect? Do they detect both an electric and a magnetic field? Do they detect only an electric field? Do they detect only a magnetic field? Or do they detect neither? And then ask the same question, but now you, the observer, are moving around with an electric charge in your hand instead of a bar magnet. So it's otherwise the same situation. So moving around with an electric charge in your hand, what do you sense? Both an electric and a magnetic field, only an electric field, only a magnetic field, or neither. So Maxwell's idea about a changing electric field can create a magnetic field prompted him to modify Ampere's law. Now, Ampere's law is basically how a current creates a magnetic field. But Maxwell said, okay, yeah, current creates a magnetic field, but we should also be able to say that just a changing electric field can create a magnetic field. And so what he did was he took Faraday's idea of using flux, a flux that changes in time. So Faraday said a magnetic flux changing in time creates an electric field. So Maxwell twisted that around and said, okay, a changing electric flux creates a magnetic field. And so he tacked on this term to Ampere's law that deals with the change in an electric flux over time, also giving rise to a magnetic field. The addition that Maxwell made to Ampere's law, along with Faraday's law, along with Gauss's law for electric fields, along with Gauss's law for magnetic fields, makes up what are known as Maxwell's equations. These equations are sufficient to describe the unification of electricity and magnetism. The equations themselves are pretty complicated. You saw the one on the previous slide, and that's pretty complicated to understand, and I'm not going to really force that on you. But the idea behind it is that electricity and magnetism are really a single phenomenon. They're the two sides of a coin. They're the same thing. Let's try and understand this in a rather easy to replicate situation, having an electric charge oscillate up and down an antenna. So that's kind of what that crude graphical depiction is representing on the left-hand side. We're going to have a charge that's oscillating up and down the metal rods that you see in the graphic. So it's a straight up and down oscillation. So the fact that there's an electric charge means that we have an electric field, and the fact that that charge is moving means we have a magnetic field. But the thing is, this magnetic field is changing in time because the charge is moving in one direction, speeding up, slowing down, switching direction. It's changing its motion all the time. And so that magnetic field is going to be changing all the time. So that magnetic field that is changing all the time creates a secondary electric field. And the way that magnetic field is changing in time causes the secondary electric field to be changing in time. And so that secondary electric field changing in time creates a secondary magnetic field. And the secondary magnetic field creates a third-order electric field. And the third-order electric field creates a third-order magnetic field, and so on and so forth. If I were to examine the electric and magnetic fields around this oscillating charge, I would get a very complicated looking figure. And the math behind it is ridiculously challenging. Obviously, we're not going to explore it, but what I want to do is I want to explore how the electric and magnetic fields change along a line. Just take a line that starts at the center of all of these oscillations and have it move straight out. And as we move along the line, we are going to examine the electric and magnetic fields. And what we get is this electromagnetic wave that we depicted in the very first slide of this lecture. Now, why are they perpendicular to each other? Well, the electric field is going to be more or less in the same direction of oscillation as the charge in the antenna. The charge oscillates up and down. The electric fields are oriented up and down. But recall that magnetic fields are perpendicular. So if the charge is moving up and down, let's say in the z direction, the magnetic field is going to be in the xy direction. It's going to be perpendicular to the direction of motion of the charge. Well, what we get is the direction of motion of the charge is parallel to the electric field. But the magnetic field is perpendicular to the direction of the charge's motion. Therefore, the magnetic field is perpendicular to the direction of the electric field associated with it. Hopefully that makes some sense as to why they're perpendicular to each other. There's also a finite speed of propagation. It's not like I can set this charge oscillating up and down in the antenna and the effects are felt immediately throughout the universe. It takes time for these effects to travel outwards, and that is based on the speed at which those effects propagate. Maxwell examined how fast these electromagnetic fields propagate outwards from the oscillating charge, and he calculated a pretty rapid speed, 2.9979 times 10 to the 8 meters per second. Notice that the equation that Maxwell generated is surprisingly simple, and it involves the constants that we've seen before. Epsilon naught, the permittivity of free space, mu naught, the permeability of free space. And we see that the speed is simply 1 over the square root of epsilon naught times mu naught. After all of those calculations, and believe me, the calculations are quite horrible, Maxwell came up with a very simple expression and came up with this value of 2.9979 times 10 to the 8 meters per second. Well, at the time Maxwell did this, the speed of light was known to be about 3 times 10 to the 8 meters per second. The problem was, light, at the time, it wasn't quite certain what light was. By the mid-1800s, when Maxwell was doing his work, it was widely accepted that light was some sort of wave-like phenomenon. But a wave of what? Maxwell came along and said, it's an electromagnetic wave. The oscillating fields make up that wave portion as the light propagates away, and the speed of, and what was Maxwell calculated for the speed happened to match up with the known speed of light. You know, Maxwell, nobody knew what light was. Maxwell says, oh look, this speed is awfully similar to the speed of light. Perhaps it's because light is an electromagnetic wave. Now, that might be coincidence, and that's why that idea wasn't widely accepted initially. Furthermore, nobody had detected electric or magnetic fields in light. It wasn't, unfortunately, until after the death of Maxwell that a German experimentalist by the name of Heinrich Hertz was able to experimentally verify the existence of electric and magnetic fields in light. And because of what he did, the unit of frequency is named after him, the Hertz. So Heinrich Hertz developed a little experiment where he basically used an LC circuit at resonance to create an electrical phenomenon across a little spark gap. And that spark gap was in the center of a rather large parabolically shaped piece of metal. And attached to that parabolically shaped piece of metal was another circuit that Hertz tuned based on the frequency, the resonant frequency of the original LC circuit. So he used this original LC circuit to create a spark, to create an electromagnetic propagation wave, and then he used that parabolic collector, if you will, to detect that wave. So in a way, this is the very first radio. It's not broadcasting anything other than the presence of a signal, but that's still brand new technology for 1890, and it wasn't long before people realized how effective this could be as radio. The speed of light, as it turns out, seems to be a constant. Now, when we say a constant, we typically talk about the speed of light in vacuum. So in space, the speed of light is 2.9979 times 10 to the 8 meters per second. That's almost the distance from the Earth to the Moon in 1 second. And so what that means is when you look at the Moon, you actually see it as it was just a little over a second ago. If the Moon were, for some reason, to spontaneously explode, it would take a second for the light from the explosion to reach us. We wouldn't see it instantaneously. The picture you see on the screen, you'll see these kind of circular arcs that look like streaks and might be flaws or something in the picture. That's actually an example of what is called gravitational lensing. The light that is smeared out is from a very distant bright light source, and in between that distant bright light source and us is a big mass. And so some of the light that is emanating from the source isn't directly towards us. It's on an angle that would normally otherwise just miss us. But the big mass in between us and the source of light causes that ray to bend. And because the ray bends, it's going to get kind of smeared out a little bit, and we see these circular arcs. But it's still speed of light, 2.9979 times 10 to the 8 meters per second in vacuum. The speed of light in vacuum has its own symbol. It is ubiquitous in so much of physics. It is the lowercase letter c. It means the speed of light. It means 2.9979 times 10 to the 8 meters per second. But light in vacuum, 2.9979 times 10 to the 8 meters per second. What about light in water? What about light in glass? What about light in acrylic? It turns out that the speed of light can be less. And the amount by which the speed of light drops in a material depends upon the dielectric constant of the material. More specifically, it depends upon the square root of the dielectric constant to a pretty good approximation. So it's not exact, but it is an approximation that the speed of an electromagnetic wave in a material is equal to the speed of an electromagnetic wave in vacuum divided by the square root of the dielectric constant. So let's take a look at that idea in action. Suppose we have light passing through a pane of glass, and this glass, there are many different types of glass with different dielectric constants. Let's say this one has a dielectric constant of 8.5. And remember that the dielectric constant is a unitless quantity. If I want the approximate speed of light, I take the speed of light in vacuum, which to three significant figures is 3.00 times 10 to the 8 meters per second, 300 million meters per second, divided by the square root of 8.5. And you should be able to show that that's equal to 1.03 times 10 to the 8 meters per second. In glass, in water, in just about any clear plastic, the speed of light is going to be on the order of 10 to the 8 meters per second. However, in very exotic circumstances, some physicists have been able to get the speed of light down to experiment in which they were able to freeze the speed of light, and they didn't have to use the force to do it. When you talk about waves, whether it's water waves, electromagnetic waves, sound waves, seismic waves, there are two quantities that join hand in hand, and those quantities are the wavelength and the frequency. You might have had waves last semester. I am not assuming that you've seen waves before this, but we do need to have an understanding of these two ideas of frequency and wavelength. The speed at which the wave propagates is equal to frequency times wavelength. Now, what are frequency and wavelength? Let's go back to that animation of an electromagnetic wave. And I'm just going to freeze it for a moment. The wavelength is the distance from the peak in one set of oscillations to the adjacent peak in the next set of oscillations. Now, don't go from a positive peak to a negative peak. You go from one positive peak to the next adjacent positive peak, and that horizontal distance you travel is the wavelength. And it should be constant throughout the entire stretch of the propagating wave. The frequency can be viewed as how fast these arrows are oscillating up and down. It's hard to see in this because it's moving very fast, but really what's happening is there is a single arrow at any given location, and that arrow is simply oscillating up and down. We actually do not have arrows propagating down the length of the direction of propagation. There's at each location, there's a single arrow that is oscillating up and down in its height. And the rate at which it oscillates up and down is called the frequency. Frequency has units of hertz. So if you talk about a frequency of 5 hertz, that means that in 1 second it oscillates down and up, goes through a full oscillation, then it goes through a second and a third and a fourth and a fifth. 5 full oscillations in 1 second. That's what 5 hertz would mean. When we talk about light, what are typical frequencies and wavelengths? How do we find them? Since we have the speed of light as a constant in vacuum, we get this fixed relationship between the frequency in a ray of light and the wavelength in a ray of light. We see that they are inverse to each other. If F goes up, lambda goes down. If lambda goes down, F goes up. So if you have something with a very high frequency, light with a very high frequency, it also has a very short wavelength. If you have a very long wavelength, you also have a very short frequency. Let's take a look at what is typical for visible light. Visible light runs the gamut of the colors of the rainbow. So we might see it at red light, and that's been measured to have a wavelength of 700 nanometers. Blue light, which is close to the other extreme of visible light, has a wavelength of about 390 nanometers. So what's the typical frequency for red? What's the typical frequency for blue? We have our equation, C equals F lambda. We are solving for frequency. Frequency equals C over lambda. Let's plug in the numbers, but we have to plug in standard units. And the standard unit for wavelength is the meter. Nano means times 10 to the negative 9. So let's take this into consideration. We get that the frequency for red light is C over the red wavelength. 3 times 10 to the 8 divided by 700 times 10 to the negative 9. Now be careful how you use your calculator. You should independently check and see that you can generate the number 4.29 times 10 to the 14, 10 to the positive 14 hertz. That is 429 billion hertz, 429 billion oscillations per second. If this were a test question, you would probably see the answer written as 429 gigahertz. With blue light, it's the same calculation, just with the different number. C is still 3 times 10 to the 8 meters per second, but now lambda, the wavelength, is 390 times 10 to the negative 9 meters. Plug it in, you should be able to get the quantity 7.69 times 10 to the 14, and that is 769 gigahertz. These sound like ridiculously high frequencies, but they are perfectly ordinary for light, for visible light. So make sure that as lambda goes up, the frequency goes down, and as lambda goes down, the frequency goes up, and you'll probably be okay. That's it for now. Take care. Bye-bye.